Imagine a computer so powerful that it could break every password on Earth in seconds. A machine that could discover new life-saving drugs in hours instead of decades. A device that operates on principles so strange, so counterintuitive, that even Albert Einstein called them spooky. This isn't science fiction. This is quantum computing, and it's happening right now. For most of human history, we've built machines that follow simple, logical rules. A light switch is either on or off. A coin shows either heads or tails. Traditional computers, the ones in your phone, your laptop, even the most powerful supercomputers in the world, all work the same way. They process information as ones and zeros, billions of tiny switches flipping on and off at incredible speeds. This has taken us far. We've mapped the human genome, connected the entire world through the internet, and sent robots to Mars. But we're hitting a wall. There are problems in our universe that are simply too complex for traditional computers to solve. Not in 1,000 years. Not in 1,000,000. Some calculations would take longer than the age of the universe itself. We're talking about simulating complex molecules for new medicines, optimizing supply chains across entire continents, modeling climate change with perfect accuracy, or cracking the encryption that protects our digital lives. These aren't just hard problems. They're impossible problems for classical computers. But what if we could build a computer that doesn't play by the same rules? What if instead of ones and zeros, we could harness the bizarre, almost magical properties of the quantum world? This is where quantum computing enters the picture. And trust me, once you understand what makes these machines different, you'll see why scientists, tech giants, and governments are racing to build them. Traditional computers are like someone trying to find the exit in a massive maze by testing every single path, one at a time. They're fast at walking down paths, sure, but they still have to check each one sequentially. A quantum computer, on the other hand, can explore all paths simultaneously. It's as if the computer exists in multiple realities at once, testing every possibility in parallel, and then collapsing into the single correct answer. This isn't an exaggeration. This is genuinely how they work. The secret lies in something called quantum mechanics, the physics of the incredibly small. At the scale of atoms and subatomic particles, the universe behaves in ways that seem to violate common sense. Particles can exist in multiple states at once. They can be connected across vast distances instantaneously. They can interfere with themselves like waves in water. For decades, these were just fascinating quirks of nature that physicists studied in laboratories. But then someone asked a revolutionary question. What if we could use these quantum properties to process information? That question has led to one of the most exciting technological races in human history. We're not just talking about faster computers. We're talking about computers that operate on fundamentally different principles, that can solve entirely new categories of problems, that could revolutionize medicine, cryptography, artificial intelligence, materials science, and fields we haven't even invented yet. Right now, quantum computers are still in their infancy. The machines that exist today are delicate, expensive, and limited in what they can do. They need to be cooled to temperatures colder than outer space. They can only run for milliseconds before errors creep in. They have dozens of quantum bits, or qubits, when we'll eventually need millions. But make no mistake, we've already crossed a threshold. In 2019, Google announced that their quantum computer had performed a calculation in minutes that would take the world's fastest supercomputer 10,000 years. IBM disputed the exact numbers, but the message was clear. Quantum advantage is real. The implications are staggering. Within your lifetime, we might see quantum computers designing perfect batteries for electric vehicles, creating artificial intelligence that truly thinks, discovering cures for diseases by simulating every molecule in the human body, or even cracking the mathematical problems that keep your credit card information safe. Some of these possibilities are exciting. Some are terrifying. All of them are coming. But here's what makes this journey so fascinating. To understand quantum computers, you don't need a physics degree. You don't need to be a mathematician. You just need to be willing to accept that the universe at its most fundamental level is far stranger and more wonderful than our everyday experience suggests. You need to be ready to question your assumptions about how reality works. Over the next couple of hours, We're going to take a deep dive into the world of quantum computing. We'll explore the mind-bending physics that makes it possible. We'll see how these machines are actually built, cooled to near absolute zero, and coaxed into performing calculations that defy logic. We'll meet the brilliant minds in major companies racing to build the first truly practical quantum computer. We'll look at the problems they'll solve and the industries they'll transform. And we'll grapple with the profound questions they raise about privacy, security, and the future of human knowledge. This is a story about pushing the boundaries of what's possible. It's about harnessing the fundamental fabric of reality itself to build machines that can compute the previously incomputable. It's about standing on the edge of a technological revolution that could be as significant as the invention of the transistor or the internet. So let's begin this journey together. Let's unlock the secrets of quantum computing and discover why this technology might just change everything we know about what computers can do. Welcome to the quantum revolution. To understand quantum computers, we need to travel down to the smallest scales of reality, where the rules that govern our everyday lives simply stop working. We need to enter the quantum realm, and I promise you, it's going to challenge everything you think you know about how the universe operates. Let's start with something familiar. Think about a coin. When you flip it, that coin is spinning through the air, and while it's in motion, you might say it's neither heads nor tails. But here's the thing. It actually is one or the other. You just don't know which yet. If you had a high-speed camera and perfect information about the flip, you could predict exactly how it would land. The uncertainty isn't in the coin. It's in your knowledge. This is how the classical world works. Things have definite states. We just might not know what they are. Now throw that logic out the window, because in the quantum world, things genuinely don't have definite states until you measure them. A quantum particle isn't just unknown before you look at it. It literally exists in multiple states simultaneously. This is called superposition, and it's the first key principle that makes quantum computing possible. Imagine you have a quantum coin. Before you look at it, it's not secretly heads or secretly tails. It's actually both heads and tails at the same time. It exists as a combination, a mixture, a superposition of both possibilities. Only when you observe it, when you measure it, does it choose to be one or the other. This isn't a limitation of our measurement tools. This is the fundamental nature of reality at the quantum scale. I know what you're thinking. This sounds absurd. How can something be two things at once? But this has been tested thousands of times in laboratories around the world. Electrons, photons, atoms, they all behave this way. The famous double-slit experiment demonstrates this beautifully. Send a single photon, a single particle of light, toward two slits. Classical logic says it must go through one slit or the other. But quantum mechanics says it goes through both slits simultaneously, creating an interference pattern with itself. Only when you try to measure which slit it went through does it collapse into going through just one. The act of observation fundamentally changes reality. For quantum computers, superposition is everything. Remember how I said a classical computer uses bits that are either 0 or 1? A quantum bit, a qubit, can be 0, 1, or both at the same time. One qubit in superposition represents two states simultaneously. 2 qubits represent 4 states. 3 qubits represent 8 states. The number doubles with each additional qubit. By the time you have just 300 qubits, you're representing more states simultaneously than there are atoms in the observable universe. This exponential scaling is the source of quantum computing's incredible power. But superposition is just the beginning. The second principle we need to understand is entanglement, and this one is even stranger. Einstein himself was so bothered by entanglement that he spent years trying to prove it couldn't be real. He called it spooky action at a distance, and he was right to be unsettled. Entanglement breaks our intuitions about how separate objects should behave. Here's how it works. When two quantum particles become entangled, they form a connection that transcends space. Measure one particle, and you instantly know something about the other, no matter how far apart they are. And we're not talking about them having predetermined states that we're just discovering. The measurement of one genuinely affects the state of the other instantaneously, even if they're on opposite sides of the galaxy. Let me give you an analogy. Though, like all analogies for quantum mechanics, it breaks down if you push it too far. Imagine you have two magic coins that are entangled. You take one to Tokyo, and I keep one in New York. Before I flip my coin, both coins are in superposition, both heads and tails simultaneously. The moment I observe my coin and it collapses to heads, your coin in Tokyo instantly collapses to tails. Not because information traveled between them, not because they were coordinated in advance, but because they're not really separate coins anymore. They're part of a single quantum system. Entanglement allows qubits in a quantum computer to be correlated in ways that classical bits simply cannot be. When you have multiple entangled qubits, they don't just represent all possible combinations independently. They represent complex correlations between those combinations. This creates a vast space of possibilities that a quantum computer can explore simultaneously. It's like having multiple players in a game who can coordinate their moves perfectly without communicating, because at a fundamental level, they're not separate players. The third key principle is quantum interference, and this is how quantum computers actually extract useful answers from all those superpositions. Remember, having a qubit in superposition of all possible states isn't useful by itself. We need to get the right answer out. This is where the wave nature of quantum particles comes into play. In quantum mechanics, particles aren't just particles. They're also waves. These waves can interfere with each other, just like ripples on a pond. When two wave peaks meet, they amplify each other. When a peak meets a trough, they cancel out. Quantum algorithms are designed to make the wrong answers interfere destructively, canceling each other out, while the right answers interfere constructively, amplifying until they're the most likely outcome when you finally measure your qubits. Think of it like this. You have 1,000 paths through a maze, and you want to find the one that leads to the exit. A classical computer checks each path one by one. A quantum computer explores all 1,000 paths simultaneously through superposition. But it doesn't just randomly pick one. The quantum algorithm is designed so that the wave functions of the wrong paths cancel each other out through interference, while the wave function of the correct path grows stronger and stronger. When you finally measure the system, you're overwhelmingly likely to get the right answer. This combination of superposition, entanglement, and interference is what gives quantum computers their extraordinary power. But it also makes them incredibly fragile. These quantum states are delicate. Any interaction with the environment, any measurement, any stray photon or vibration can cause decoherence, where the quantum properties collapse and you're left with just another classical system. This is why quantum computers need to be isolated from the outside world so carefully. There's another crucial concept called quantum tunneling that plays a role in certain types of quantum computers. In the classical world, if you don't have enough energy to climb over a hill, you can't get to the other side. You're stuck. But quantum particles can sometimes pass through barriers that they shouldn't be able to cross according to classical physics. They literally tunnel through them. There's a probability that the particle will appear on the other side of the barrier without ever having enough energy to go over it. For certain quantum computing approaches, especially quantum annealing, tunneling allows the system to explore solution spaces more efficiently. Instead of having to climb over every peak in a complex landscape to find the lowest valley, the system can tunnel through peaks, potentially finding optimal solutions faster than classical algorithms that have to navigate the landscape step by step. Now, here's something that often confuses people. Quantum mechanics is probabilistic. When you measure a qubit, you get a probability of finding it in one state or another. This doesn't mean quantum computers just guess randomly. The probabilities aren't arbitrary. They're precisely controlled by the quantum algorithm. A well-designed quantum algorithm runs the calculation many times, and the correct answer appears with high probability, while wrong answers appear rarely. It's like loading dice, but doing it with the fundamental laws of physics. The mathematics behind all of this is beautiful and complex. Quantum states are described by wave functions, mathematical objects that contain all the information about a system. These wave functions evolve according to the Schrödinger equation, one of the fundamental equations of quantum mechanics. When you measure a quantum system, the wave function collapses according to the Born rule, giving you specific outcomes with specific probabilities. But you don't need to understand the math to grasp the key insight. The quantum world operates on fundamentally different principles than the world we experience in our daily lives. Particles can be in multiple states simultaneously. Distant particles can be connected in ways that transcend space. Wave-like interference can amplify right answers and cancel wrong ones. These aren't just theoretical curiosities. They're real physical phenomena that we can harness to perform computations that classical computers cannot. What's truly mind-bending is that these principles have been verified experimentally countless times. Superposition, entanglement, interference, tunneling. These aren't speculation. They're observed facts about how our universe works at the smallest scales. Quantum computers aren't based on theory. They're based on repeatedly confirmed experimental reality. We're not hoping these principles work. We know they do. The challenge now is engineering systems that can exploit them reliably at useful scales. This is the foundation. This is the quantum mechanical bedrock upon which quantum computers are built. In the classical world, information is binary, definite, and local. In the quantum world, information can be superposed, entangled, and non-local. Classical computers manipulate bits. Quantum computers manipulate quantum states. Classical algorithms follow step-by-step logic. Quantum algorithms orchestrate interference patterns in possibility space. Understanding these principles is crucial because everything else about quantum computers, the hardware, the algorithms, the applications, the limitations, flows from these fundamental quantum mechanical properties. We're not just building faster computers. We're building computers that operate on the deepest laws of physics, that harness the inherent weirdness of reality itself to solve problems in entirely new ways. And now that you understand the foundation, we can start building upward to see exactly how these remarkable machines actually work. Now that we understand the quantum mechanical principles, let's talk about how you actually build a machine that can harness these bizarre properties. How do you take superposition, entanglement, and interference and turn them into a working computer? This is where theory meets engineering, and the challenges are enormous. At the heart of every quantum computer is the qubit, the quantum bit. Unlike a classical bit that's definitively 0 or 1, a qubit can exist in a superposition of both states simultaneously. But what actually is a qubit? It's not some exotic new particle. It's any quantum system that has two distinct states we can use to represent 0 and 1. The art of building quantum computers is finding physical systems that can maintain quantum properties long enough to perform useful calculations. Let's start with one of the most common approaches, superconducting qubits. These are what companies like IBM, Google, and Rigetti use in their quantum computers. Imagine a tiny electrical circuit, smaller than a human hair, made from materials that become superconducting when cooled to near absolute zero. In a superconductor, electrical current flows without any resistance whatsoever. Electrons pair up and move through the material as a quantum wave, behaving more like a single quantum object than individual particles. In a superconducting qubit, you create a loop of superconducting wire with a special component called a Josephson junction. This junction acts like a quantum switch. The current in the loop can flow clockwise, counterclockwise, or both simultaneously in superposition. Clockwise represents 0, counterclockwise represents 1, and superposition gives you both. You control these qubits by hitting them with precisely tuned microwave pulses, which rotate their quantum states in carefully orchestrated ways. Think of it like conducting an orchestra, but instead of musicians, you're conducting quantum states, and instead of music, you're performing calculations. The challenge with superconducting qubits is that they're incredibly sensitive. They need to be kept at temperatures around 15 millikelvin. That's 15 thousandths of a degree above absolute zero. Colder than the vacuum of space. Why so cold? Because heat is just random motion of particles, and that random motion destroys the delicate quantum states. Even a single stray photon of heat can cause decoherence, collapsing your superposition and ruining your calculation. These machines require massive dilution refrigerators with multiple cooling stages, each one progressively colder, looking like golden chandeliers of quantum technology. Another popular approach uses trapped ions. This is the technology behind companies like IonQ and Honeywell. Instead of electrical circuits, These systems use individual atoms, typically ions of elements like ytterbium or calcium. The ions are held in place by electromagnetic fields in an ultra-high vacuum chamber, suspended in space like pearls on a string of light. Each ion is a qubit. You manipulate them using precisely tuned laser beams that can flip their quantum states or create entanglement between them. Trapped ion systems have some beautiful advantages. Individual atoms are nature's perfect qubits. Every ytterbium ion in the universe is identical, which means your qubits are all perfectly manufactured. They also maintain their quantum properties for relatively long times, sometimes several seconds, which is an eternity in quantum computing terms. The laser control is extremely precise, allowing for very accurate quantum operations. The downside: these systems are complex to build and scale. Controlling dozens of lasers with picosecond timing while keeping ions perfectly trapped is an extraordinary engineering challenge. Then there are photonic quantum computers, which use particles of light, photons, as qubits. Companies like Xanadu and PsiQuantum are pursuing this approach. A photon's quantum state might be encoded in its polarization, whether it's vibrating vertically or horizontally, or in which path it takes through an optical circuit. The advantage of photonic systems is that photons don't interact with each other or their environment very easily, which means they maintain quantum coherence well. They can also operate at room temperature, avoiding the massive cooling requirements of superconducting systems. The challenge is creating and detecting single photons reliably, and getting them to interact with each other in controlled ways to perform quantum operations. There are even more exotic approaches being explored. Topological qubits, which companies like Microsoft are researching, would encode quantum information in exotic particles called anyons. These would theoretically be much more resistant to errors because the quantum information is stored in the topology, the global properties of the system, rather than in local states that can be easily disturbed. Neutral atom systems trap clouds of neutral atoms in optical tweezers and manipulate them with lasers. Silicon spin qubits encode information in the spin of individual electrons trapped in silicon, potentially allowing quantum computers to be built using modified versions of existing semiconductor technology. Each approach has trade-offs between coherence time, how long quantum states last, gate fidelity, how accurately you can perform operations, connectivity, how easily qubits can interact with each other, and scalability, how feasible it is to build systems with thousands or millions of qubits. There's no clear winner yet, and it's entirely possible that different approaches will be optimal for different types of problems. But regardless of the physical implementation, all quantum computers share the same basic architecture. You have your qubits, your quantum memory. You have a way to initialize those qubits into a known starting state, typically all zeros. You have quantum gates, operations that manipulate the quantum states of one or more qubits. And you have a measurement system that collapses the quantum states and reads out the final result. Quantum gates are the building blocks of quantum algorithms, analogous to the logic gates in classical computers. But quantum gates are fundamentally different. A classical gate like and or takes definite inputs and produces definite outputs. A quantum gate takes superpositions as inputs and produces entangled superpositions as outputs. It's performing operations on probability amplitudes, the mathematical objects that describe quantum states. The most basic single-qubit gates rotate the quantum state around the Bloch sphere, a geometric representation of a qubit's possible states. The Pauli-X gate flips a qubit from 0 to 1, or vice versa. The Hadamard gate puts a qubit into an equal superposition of 0 and 1. The phase gates change the relative phase between the 0 and 1 components of a superposition, which affects how they'll interfere later. But the real power comes from two-qubit gates that create entanglement. The most famous is the CNOT gate, the controlled NOT gate. It flips the state of one qubit only if another qubit is in the one state. When applied to superpositions, this creates entanglement between the qubits. There are other two-qubit gates like the swap gate and controlled phase gates, each creating different patterns of entanglement and interference. A quantum algorithm is essentially a sequence of these gates applied to your qubits. You initialize your qubits, Apply a series of single and two-qubit gates in a carefully designed pattern, and then measure the results. The art of quantum algorithm design is figuring out which sequence of gates will create the right interference pattern so that wrong answers cancel out and right answers amplify. Here's where things get really challenging. Every time you apply a gate, there's some probability of error. The qubit might not rotate exactly the right amount. Stray electromagnetic fields might introduce unwanted phases. Two qubits might not entangle perfectly. These errors accumulate. After dozens or hundreds of gates, your quantum state might be completely corrupted by noise. Current quantum computers have error rates of around 1 error per 100 or 1,000 operations. That sounds pretty good until you realize that useful quantum algorithms might require millions or billions of operations. If every 100th operation has an error, your calculation will be completely wrong long before you finish. This is the fundamental challenge facing quantum computing today. The solution is quantum error correction, and it's both elegant and expensive. The basic idea is to encode a single logical qubit, the qubit you actually want to compute with, into multiple physical qubits. If one physical qubit develops an error, you can detect and correct it without destroying the quantum information in the logical qubit. This is remarkably difficult to achieve because measuring a quantum state normally collapses it. But clever error correction codes allow you to measure whether an error occurred without learning what the actual quantum state is. The most promising error correction schemes require encoding one logical qubit into dozens, hundreds, or even thousands of physical qubits. The surface code, one of the leading candidates, might need 1,000 physical qubits per logical qubit. This means that to run an algorithm with 1,000 logical qubits, you'd need around 1,000,000 physical qubits. Current quantum computers have tens to hundreds of qubits. The gap is enormous. This leads us to an important distinction in the current quantum computing landscape. We have noisy intermediate-scale quantum computers, or NISQ devices. These are the quantum computers that exist today. They have 50 to a few hundred qubits, limited connectivity, and no error correction. They can run short quantum algorithms before errors overwhelm the calculation. They're incredibly valuable for research, for learning how to control quantum systems, and for exploring what near-term quantum computers might be able to do. But they're not yet the fault-tolerant quantum computers of the future. Fault-tolerant quantum computers will have full error correction, allowing them to run arbitrarily long quantum algorithms with arbitrary accuracy. These machines might have millions or tens of millions of physical qubits implementing thousands of logical qubits. They'll be able to run Shor's algorithm to factor large numbers, breaking modern encryption. They'll simulate complex quantum systems for drug discovery and material science. They'll optimize massive systems and accelerate machine learning. But building fault-tolerant quantum computers requires solving enormous engineering challenges. Let's talk about coherence time and gate time, two critical metrics. Coherence time is how long a qubit can maintain its quantum properties before decoherence destroys them. Gate time is how long it takes to perform a quantum operation. The ratio between these determines how many operations you can perform before losing your quantum state. For superconducting qubits, coherence times are measured in microseconds, while gate times are nanoseconds, giving you thousands of possible operations. For trapped ions, coherence times can be seconds, while gate times are microseconds, giving you millions of possible operations. But you need millions to billions of operations for useful algorithms, which is why error correction is essential. Different quantum computing architectures also differ in qubit connectivity. In some systems, like trapped ions with their string of atoms, every qubit can directly interact with every other qubit, giving you all-to-all connectivity. In superconducting systems, qubits are physically laid out on a chip, and each qubit can only directly interact with its nearest neighbors. To entangle distant qubits, you need to perform sequences of swap operations to move quantum states around, adding time and introducing more opportunities for errors. This is like the difference between everyone in a meeting being able to talk to everyone else versus only being able to talk to the person next to you. The control systems for quantum computers are themselves marvels of engineering. You need to generate precisely timed control pulses, sometimes thousands of them per second. each one tuned to the exact frequency and phase needed to manipulate specific qubits. 4 superconducting systems. This means sophisticated microwave electronics operating at cryogenic temperatures. 4 ion traps. It means laser systems with incredible stability and precision. The classical computers, controlling quantum computers, are themselves quite powerful, running real-time feedback loops that adjust control pulses based on measurement results. Calibration is another massive challenge. The properties of qubits drift over time due to temperature fluctuations, stray electromagnetic fields, and other environmental factors. Before running a quantum program, you need to calibrate the system, determining the exact frequencies and pulse shapes needed to perform each gate accurately. This calibration might need to be repeated every few hours or even more frequently. Advanced quantum computers are constantly calibrating themselves, learning and adapting to maintain optimal performance. There's also the question of how you actually program a quantum computer. You can't just write code like you would for a classical computer. Well, you can, but underneath it's very different. Quantum programming languages like Qiskit from IBM, Cirq from Google, or Q# from Microsoft let you specify quantum circuits, sequences of gates applied to qubits. You describe which qubits to initialize, which gates to apply in what order, and which qubits to measure at the end. The quantum development kit then compiles this into the actual control pulses sent to the hardware. Higher-level quantum programming tries to abstract away some of these details, letting you think in terms of quantum algorithms rather than individual gates. But quantum programming remains fundamentally different from classical programming. You're not writing instructions to be executed step by step. You're designing interference patterns in quantum state space. Understanding how quantum computers actually work reveals both their incredible potential and their current limitations. These machines are exploiting fundamental physics at the edge of what's possible. Every qubit needs to be exquisitely isolated from its environment while simultaneously being precisely controllable. Every gate needs to be performed with incredible accuracy. Error correction requires massive overhead. Scaling to useful sizes demands solving multiple hard problems simultaneously. But here's what's remarkable. Despite all these challenges, we've built working quantum computers. They're small and noisy, but they're real. Researchers can log into cloud-based quantum computers and run their own quantum algorithms. Companies are investing billions in scaling up these systems. The engineering problems are immense, but they're problems of execution, not of fundamental physics. We know quantum computers can work because we've built them. Now it's a matter of building bigger, better, more reliable versions. And that journey from prototype to practical quantum computer is happening right now, faster than many expected. Let's step inside a quantum computing lab and see what these machines actually look like. Forget the sleek laptops and server racks of classical computing. Quantum computers are some of the most complex and exotic machines humanity has ever built, and the engineering required to make them work is absolutely staggering. Walk into a room with a superconducting quantum computer, and the first thing you'll see is the dilution refrigerator. It looks like a massive golden chandelier, hanging from the ceiling, sometimes 2 or 3 meters tall. This isn't decoration. This is one of the most sophisticated cooling systems on Earth, and it needs to be. To operate superconducting qubits, you need temperatures around 15 millikelvin. That's 15 thousandths of a degree above absolute zero, about 200 times colder than the coldest temperature ever recorded in space. Why so cold? Remember that superconducting qubits rely on the quantum properties of superconducting materials. At normal temperatures, thermal energy constantly jostles electrons around. Even at liquid nitrogen temperatures, 77 Kelvin or negative 196 Celsius, there's far too much thermal noise. Only at these extreme cryogenic temperatures do the thermal fluctuations become small enough that quantum states can survive for useful amounts of time. Getting to these temperatures requires multiple stages of cooling. The dilution refrigerator has several temperature stages, each one progressively colder. You might start with a stage at 4 Kelvin, cooled by liquid helium, then a stage at 1 Kelvin, then 100 millikelvin. Finally, you reach the mixing chamber at the bottom where temperatures drop to 15 millikelvin or even lower. Each stage is carefully designed to minimize heat transfer to the stages below, while still allowing the quantum processor and its control lines to pass through. The quantum processor itself sits at the very bottom of this refrigerator, in what's called the coldest place in the universe. It's a chip, often just a few centimeters across, made from materials like niobium or aluminum deposited on a sapphire or silicon substrate. On this tiny chip are etched the superconducting circuits that form the qubits, arranged in carefully designed patterns. If you could see them under a microscope, you'd see serpentine paths of metal, capacitors, and those crucial Josephson junctions, all smaller than the human hair. But the chip itself is just the beginning. Connected to it are dozens or hundreds of control lines, thin coaxial cables that snake up through the various temperature stages of the refrigerator. These cables carry microwave signals down to control the qubits and read out signals back up to room temperature electronics. Each cable is carefully engineered to minimize heat transfer while maintaining signal quality. Some cables have attenuators at different temperature stages to reduce noise. Some have circulators to ensure signals only flow in one direction. The engineering of these control lines is an art form in itself. At room temperature, racks of electronics generate the control pulses. Arbitrary waveform generators create precisely shaped microwave pulses, each one tuned to the frequency of a specific qubit. These frequencies are in the gigahertz range, billions of cycles per second, and they need to be controlled with incredible precision. The timing between pulses needs to be accurate to nanoseconds. The phase relationships need to be maintained, and all of this needs to be coordinated across potentially hundreds of channels simultaneously. Shielding is absolutely critical. The quantum processor needs to be isolated from electromagnetic radiation, which can cause decoherence. The dilution refrigerator is surrounded by layers of shielding, some made of special magnetic materials that block magnetic fields, others that block electromagnetic radiation. Even the Earth's magnetic field needs to be carefully compensated. A stray cell phone signal, a radio station, even the electromagnetic noise from nearby electrical equipment can potentially disrupt the delicate quantum states. Now let's look at trapped ion systems, which have a completely different architecture. Instead of cooling to near absolute zero, these systems use ultra-high vacuum chambers. The vacuum needs to be extreme, around 10 to the negative 11 torr or better, which means there are almost no gas molecules left in the chamber. Why? Because any collision between an ion and a stray molecule can disturb the ion's quantum state. At these vacuum levels, an ion might go hours or days without encountering a gas molecule. Inside the vacuum chamber is the ion trap itself, often a beautiful piece of engineering made from gold-plated electrodes precisely machined and positioned. These electrodes create electric fields that hold the ions in place, suspended in vacuum like beads on a string. The ions are typically arranged in a line, each one separated from its neighbors by a few micrometers. You can actually see them if you shine the right light on them. They fluoresce, glowing like tiny stars in the darkness of the vacuum chamber. Controlling trapped ions requires lasers, lots of them. You need lasers to cool the ions, bringing them to temperatures just microkelvins above absolute zero, even though they're not physically touching anything cold. This is laser cooling, where carefully tuned laser light removes energy from the ions. You need lasers to manipulate the qubit states, driving quantum transitions with precise pulses of light. You need lasers for readout, shining light on the ions and detecting whether they fluoresce or not to determine their quantum state. These aren't off-the-shelf lasers. They're highly stable, frequency lock systems, where the laser frequency is controlled to better than 1 part in a trillion. The laser beams are shaped, focused, and directed using complex optical systems. Acousto-optic modulators split single laser beams into multiple beams, each one aimed at a different ion, each one carrying independent control signals. The optical tables holding all this equipment are massive, covered with mirrors, lenses, beam splitters, and other optical components, all carefully aligned. Some trapped ion systems are moving toward integrated photonics, where the optical components are etched onto chips rather than assembled from discrete components on optical tables. This could make the systems more compact and stable, potentially enabling trapped ion quantum computers that fit in a single rack rather than filling entire rooms. Photonic quantum computers have yet another architectural approach. These systems generate and manipulate individual photons, particles of light. Sources generate single photons on demand, often using quantum dots or nonlinear optical processes. These photons are then routed through integrated photonic circuits, chips with waveguides etched into them that guide light the way wires guide electricity. Inside these photonic circuits are beam splitters, phase shifters, and other components that manipulate the photon's quantum states. The photons need to arrive at specific components at precisely the right times, which requires controlling path lengths to fractions of a wavelength. At the end, single photon detectors measure which paths the photons took or what polarization they have, extracting the results of the quantum computation. One advantage of photonic systems is that they can potentially operate at room temperature or with only modest cooling. The photons themselves don't need to be cold because they don't interact much with their environment. However, some of the best single photon detectors need to be cooled to cryogenic temperatures to reduce noise, and generating high-quality single photons on demand remains challenging. Regardless of the physical platform, all quantum computers face the same fundamental challenge: maintaining quantum coherence long enough to perform useful computations while still being able to control the qubits precisely. This is like trying to conduct a symphony in the middle of an earthquake. You need incredibly fine control, but the slightest disturbance can ruin everything. Error correction, which we touched on earlier, requires even more sophisticated hardware. To implement error correction, you need many physical qubits per logical qubit, and you need to constantly measure syndrome qubits to detect errors without collapsing the logical quantum state. This means more qubits, more control lines, more measurement apparatus, all while maintaining or improving coherence times and gate fidelities. Some research groups are exploring three-dimensional architectures to fit more qubits into a given space and improve connectivity. Instead of flat chips, these systems stack multiple layers of qubits or arrange them in complex three-dimensional structures. Others are developing new materials with better superconducting properties or less sensitivity to noise. The fabrication of quantum processors is itself an extraordinary challenge. These chips are made in specialized cleanrooms, some of the most advanced fabrication facilities on Earth. The processes are similar to those used for classical computer chips, but with additional requirements. For superconducting qubits, you need to deposit extremely pure superconducting films, pattern them with nanometer precision, and create Josephson junctions with exactly the right properties. A single defect, a single impurity, can create a source of noise that degrades qubit performance. Quality control is intense. Not every chip that comes out of fabrication works well. Some qubits might have poor coherence times. Some gates might have high error rates. Companies fabricate many chips and select the best ones for their quantum computers. As the field matures, fabrication yields are improving, but it remains a significant challenge. The classical control systems are often underappreciated but absolutely essential. Modern quantum computers have sophisticated real-time feedback systems. Measurement results can be processed in microseconds, and subsequent control pulses can be adjusted based on those results. This enables mid-circuit measurement, where you measure some qubits in the middle of an algorithm and use those results to decide what gates to apply next. This is crucial for error correction and for certain quantum algorithms. Power requirements vary dramatically by platform. A superconducting quantum computer might consume tens of kilowatts, mostly to run the dilution refrigerator and the room temperature control electronics. Trapped ion systems consume power for vacuum pumps, laser systems, and control electronics. Photonic systems might have lower power requirements, but that depends on the specific implementation and whether cooling is needed. There's also the question of system reliability and uptime. Early quantum computers were research instruments that might run for a few hours at a time before needing recalibration or maintenance. Modern quantum computers aim for much higher uptime, with some cloud-accessible systems available more than 90% of the time. This requires robust hardware, automated calibration procedures, and sophisticated diagnostics to detect and correct problems. Some companies are exploring modular architectures, where multiple quantum processors are linked together. This could enable scaling beyond what's possible with a single processor. However, connecting quantum processors requires either flying qubits, moving quantum states from one processor to another, or generating entanglement between processors, both of which are technically challenging. The facilities housing quantum computers are themselves impressive. They need stable temperatures, low vibration, electromagnetic shielding, and reliable power. Some quantum computers are installed in specially designed rooms with spring-loaded floors to isolate them from vibrations. Others are in underground labs to reduce cosmic ray impacts, high-energy particles from space that can occasionally disrupt quantum states. Maintenance and operation require highly skilled teams. Physicists, engineers, and technicians work together to keep these systems running. Calibration might need to happen daily or even more frequently. Hardware components occasionally fail and need replacement. The dilution refrigerator might need refilling with helium every few weeks. Laser systems need alignment checks. It's a continuous process of monitoring, adjusting, and optimizing. Cost is significant. A state-of-the-art dilution refrigerator might cost hundreds of thousands of dollars. A complete superconducting quantum computer system with all the control electronics and infrastructure could cost tens of millions. Trapped ion systems have comparable costs when you factor in all the laser systems and vacuum equipment. This is why most quantum computing access is currently through cloud services rather than institutions buying their own hardware. Yet despite these enormous challenges and costs, the hardware is improving rapidly. Coherence times are increasing. Gate fidelities are improving. Qubit counts are growing. Companies are developing next-generation systems with better performance and reliability. What seemed impossible a decade ago is now routine. What seems like the cutting edge today will likely seem primitive a decade from now. The hardware of quantum computers represents some of the most ambitious engineering projects in human history. These machines operate at the intersection of quantum physics, materials science, electrical engineering, optics, and computer science. They push the boundaries of what's technically possible, requiring innovations across multiple fields simultaneously. And yet, remarkably, they work. We've built machines that genuinely harness quantum mechanics to perform computations. The question now isn't whether quantum computers are possible. It's how quickly we can make them practical, scalable, and powerful enough to change the world. Copia publica. Hardware is only half the story. The real magic of quantum computing comes from quantum algorithms, the recipes that tell quantum computers what to do. These algorithms are fundamentally different from anything you've seen in classical computing, and some of them offer speedups so dramatic they seem almost like magic. Let's explore the most important quantum algorithms and understand what makes them so powerful. The most famous quantum algorithm is Shor's algorithm, developed by mathematician Peter Shor in 1994. This algorithm can factor large numbers exponentially faster than the best-known classical algorithms, and it's the reason why quantum computers threaten modern cryptography. To understand why this matters, we need to talk about factoring and encryption. Factoring means breaking a number down into its prime factors. If I give you the number 15, you can easily tell me it's 3 times 5. But if I give you a number with hundreds of digits, finding its prime factors becomes extraordinarily difficult. The best classical algorithms require time that grows exponentially with the number of digits. For a 200-digit number, factoring could take longer than the age of the universe, even with the world's most powerful supercomputers. This difficulty is the foundation of RSA encryption, which protects everything from your credit card transactions to government communications. RSA works by multiplying 2 large prime numbers together to create a public key. The private key is those 2 original primes. Anyone can encrypt a message with the public key, but decrypting it requires knowing the private key, which means factoring that large number back into its prime components. As long as factoring is hard, RSA is secure. Shor's algorithm changes everything. On a sufficiently large quantum computer, it can factor numbers in polynomial time, which grows much more slowly than exponential time. A quantum computer with a few thousand logical qubits could factor a 200-digit number in hours or days instead of billions of years. This means RSA encryption would become obsolete. Every message ever encrypted with RSA could theoretically be decrypted. The implications for cybersecurity are profound. How does Shor's algorithm work? It's beautifully clever. The algorithm transforms the factoring problem into a period-finding problem. It turns out that if you can find the period of a certain mathematical function related to the number you want to factor, you can use that period to find the factors. Classical computers struggle with period finding for large numbers, but quantum computers excel at it. The algorithm uses quantum Fourier transform, a quantum version of the classical Fourier transform that decomposes signals into their frequency components. The quantum version can be implemented efficiently with quantum gates, and it's the key to extracting the period from the quantum state. Through superposition, the quantum computer essentially evaluates the function at many inputs simultaneously. Through interference, it amplifies the period information while canceling out other information. When you measure the final state, you get information about the period, which you can then use classically to find the factors. Shor's algorithm isn't just about breaking encryption. It's a proof of concept that quantum computers can solve problems exponentially faster than classical computers. It showed the world that quantum computing isn't just theoretical curiosity, but a genuine computational paradigm shift. Another landmark algorithm is Grover's algorithm, developed by Love Grover in 1996. While not as dramatic as Shor's exponential speedup, Grover's algorithm provides a quadratic speedup for searching unsorted databases, and it has incredibly broad applications. Imagine you have a phone book with 1 million names, but it's not alphabetized. You're looking for a specific person, and the only way to find them classically is to check each entry one by one. On average, you'd need to check 500,000 entries. In the worst case, you'd check all million. This is linear search, and it's the best you can do classically without additional structure. Grover's algorithm can find the entry in roughly 1,000 steps, the square root of 1,000,000. It achieves this through a process called amplitude amplification. The algorithm puts all possible entries into superposition, then repeatedly applies an operation that amplifies the amplitude of the correct answer while reducing the amplitudes of wrong answers. After the right number of iterations, when you measure, you're highly likely to get the correct answer. The power of Grover's algorithm extends far beyond database search. Any problem that can be framed as finding a needle in a haystack can potentially benefit. This includes constraint satisfaction problems, where you're looking for solutions that satisfy certain conditions. It includes cryptographic key search, where you're trying to find a decryption key. It includes optimization problems, where you're searching for the best solution among many possibilities. Quantum simulation is another crucial application, and in some ways, it's the most natural use of quantum computers. The physicist Richard Feynman originally proposed quantum computers specifically for this purpose. He realized that simulating quantum systems on classical computers is extraordinarily difficult because the amount of information needed to describe a quantum system grows exponentially with the number of particles. A classical computer trying to simulate just 30 entangled particles needs to track billions of probability amplitudes. Simulating 100 particles requires more numbers than there are atoms in the universe. This makes simulating complex molecules, chemical reactions, or quantum materials essentially impossible classically beyond very small systems. But a quantum computer is itself a quantum system. Simulating another quantum system becomes natural. You map the quantum system you want to study onto the qubits of your quantum computer. The evolution of the qubits mimics the evolution of the system you're simulating. This could revolutionize chemistry, materials science, and drug discovery. Want to understand how a new drug candidate interacts with the protein in the body? That interaction is fundamentally quantum mechanical, involving the behavior of electrons in molecular orbitals. Classical computers can only approximate this, using simplified models that might miss crucial effects. A quantum computer could simulate the interaction exactly, revealing how strongly the drug binds, what side effects it might have, and how to modify it for better performance. Want to design a better battery? The electrochemical processes in batteries involve quantum effects in complex materials. Simulating these exactly could help identify new electrode materials or electrolytes with superior properties. Want to understand high-temperature superconductors, materials that could revolutionize power transmission? Their behavior emerges from complex quantum interactions that classical computers struggle to model. The algorithms for quantum simulation vary depending on what you're simulating. Some use the quantum phase estimation algorithm to extract energy levels of quantum systems. Others use variational quantum eigensolver, or VQE, which is particularly well suited to near-term quantum computers because it's more tolerant of noise. VQE uses a hybrid approach, where a quantum computer prepares quantum states and measures them, while a classical computer optimizes the parameters to minimize energy or some other quantity. Quantum annealing takes a different approach to optimization problems. Instead of applying sequences of gates, quantum annealing systems start with qubits in a superposition of all possible states, representing all possible solutions. They then slowly evolve the system, letting it settle into the lowest energy state, which corresponds to the optimal solution. Quantum tunneling allows the system to escape local minima and potentially find better solutions than classical optimization algorithms. Companies like D-Wave have built specialized quantum annealers with thousands of qubits. These aren't universal quantum computers. They can't run Shor's algorithm or general quantum circuits. But for certain optimization problems, like scheduling, logistics, financial portfolio optimization, or machine learning, they can potentially find good solutions faster than classical approaches. The Quantum Approximate Optimization Algorithm, or QAOA, is a gate-based version designed for near-term quantum computers. It applies alternating layers of gates, some encoding the problem and others providing mixing to explore the solution space. By varying the parameters and measuring the results, you can often find good solutions to optimization problems even with noisy qubits and limited gate depth. Quantum machine learning is an emerging field exploring how quantum computers might accelerate artificial intelligence. Some quantum algorithms could speed up linear algebra operations that are fundamental to machine learning. Others could find patterns in data more efficiently or train models faster. The quantum kernel method maps data into high-dimensional quantum state spaces, where patterns might be more easily separable. There's quantum principal component analysis, which could extract the most important features from large datasets exponentially faster than classical methods. There's quantum support vector machines for classification. There's quantum neural networks, though these are still very much in the research phase, and it's unclear whether they'll offer genuine advantages over classical neural networks for practical problems. One intriguing algorithm is the HHL algorithm for solving systems of linear equations. Many scientific and engineering problems reduce to solving equations like Ax equals B, where A is a matrix, X is the unknown vector you're solving for, and B is a known vector. For large systems with millions or billions of variables, this becomes computationally expensive. The HHL algorithm, named after its inventors Harrow, Hasidim, and Lloyd, can solve these systems exponentially faster than classical algorithms under certain conditions. The caveat is that the speedup applies to producing a quantum state representing the solution, not extracting all the numbers classically. For some applications, like using the solution in further quantum computations, this is perfect. For others where you need explicit numerical values, the advantage may be less clear. This pattern appears frequently in quantum algorithms. Exponential speedups often come with caveats about what form the output takes. Quantum walks are another algorithmic primitive with various applications. These are quantum versions of random walks, where a particle randomly steps in different directions. In the quantum version, the walker exists in superposition over different positions and can interfere with itself. Quantum walks can sometimes reach target locations quadratically faster than classical random walks, and they've been used as building blocks for search algorithms, optimization algorithms, and more. The Deutsch-Jasa algorithm was one of the first quantum algorithms demonstrating a speedup, though for a somewhat contrived problem. It determines whether a function is constant or balanced using just one query, while classically you might need many queries. While not practically useful, it was a crucial proof of concept that quantum computers could outperform classical ones. More recently, Researchers have developed quantum algorithms for graph problems, for number theory, for differential equations, and for countless other domains. Some offer exponential speedups, others polynomial speedups, others constant factor improvements. The field of quantum algorithms is vibrant and growing, with new algorithms being discovered regularly. But here's something crucial to understand. Quantum computers are not universally faster than classical computers. They're not magic boxes that speed up everything. For many problems, classical algorithms are just as good or better. Quantum speedups exist for specific problem structures, where quantum properties like superposition and interference can be exploited. Moreover, quantum algorithms are often probabilistic. They might give you the right answer with high probability, but not certainty. Running them multiple times and taking the most common answer, or using error-detecting codes, can increase confidence. But this probabilistic nature is fundamentally different from classical algorithms that deterministically produce the correct answer. Quantum algorithms also often have requirements that limit their practical applicability. They might need fault-tolerant quantum computers with thousands of logical qubits, which don't exist yet. They might need the input data to be in quantum form, which could require expensive quantum RAM. They might need problem instances with specific mathematical structure to achieve the theoretical speedups. There's ongoing debate about quantum advantage, the point at which quantum computers outperform classical computers on practical problems. Google's 2019 result demonstrated quantum supremacy on a specific sampling task, but that task was designed to be hard for classical computers and has no practical application. True quantum advantage for useful problems remains elusive, though many researchers believe it's coming soon for certain applications, like quantum chemistry simulation. The development of new quantum algorithms is both an art and a science. Researchers need deep understanding of quantum mechanics, classical algorithms, and the specific problem domain. They need to figure out how to encode problems into quantum states, design gate sequences that create the right interference patterns, and extract useful information from measurements. It's a challenging field, but the potential rewards are enormous. As quantum hardware improves, we'll likely see a coevolution of algorithms and hardware. Algorithms will be designed to match the capabilities and limitations of available hardware. Hardware will be optimized for important algorithms. Near-term algorithms might focus on what's possible with NISQ devices, while long-term algorithms assume fault-tolerant quantum computers. The most exciting possibility is that we haven't yet discovered the killer application of quantum computing. Shor's algorithm surprised everyone by showing that quantum computers could break cryptography. Maybe there's another problem domain where quantum computers will prove transformative in ways we haven't imagined. As more researchers gain access to quantum computers and explore what they can do, we may discover new algorithms and applications that we never anticipated. Quantum algorithms are the bridge between quantum hardware and real-world impact. They're how we harness the strange properties of quantum mechanics to solve problems that matter. And as we continue to develop both better algorithms and better hardware, the range of problems quantum computers can tackle will only grow. The age of practical quantum algorithms is just beginning. Now let's move from abstract algorithms to concrete applications. How will quantum computers actually change the world? What problems will they solve? And which industries will be transformed? The answers are both exciting and surprising, touching everything from the medicines you take to the security of your bank account. Let's start with drug discovery and pharmaceutical research, one of the most promising near-term applications. Developing a new drug currently takes over a decade and costs billions of dollars. Much of that time and money goes into understanding how potential drug molecules interact with their targets in the body, usually proteins involved in disease. These interactions are fundamentally quantum mechanical, determined by how electrons arrange themselves in molecular orbitals. Classical computers can simulate small molecules reasonably well, but they struggle with anything complex. A drug molecule might have dozens of atoms. The protein it targets might have thousands. Simulating their interaction accurately, accounting for all the quantum effects, is simply beyond classical computing capabilities. Instead, pharmaceutical companies use approximations, simplified models, and enormous amounts of experimental trial and error. Quantum computers could change this completely. By accurately simulating molecular interactions, they could predict how strongly a drug candidate binds to its target, whether it might have side effects by binding to other proteins, and how to modify its structure for better performance. This could dramatically accelerate drug discovery and reduce costs. Instead of synthesizing and testing thousands of candidate molecules in a lab, you could screen them virtually on a quantum computer, only making the most promising ones. This isn't just theoretical. Companies like Moderna and Biogen are already partnering with quantum computing firms to explore drug discovery applications. Early projects focus on simulating specific molecules related to diseases like cancer, Alzheimer's, and infectious diseases. While we're still years away from designing drugs entirely on quantum computers, the foundational work is happening now. Materials science is another area ripe for quantum disruption. Every material around you, the steel in buildings, the silicon in computer chips, the lithium in batteries, has properties determined by quantum mechanics. Understanding why materials have the properties they do, and designing new materials with desired properties, requires simulating quantum behavior at the atomic scale. Want to design a room-temperature superconductor? Such a material would revolutionize electrical grids, eliminating transmission losses and enabling completely new technologies. But discovering it requires understanding the complex quantum interactions in materials. Want better solar cells that convert more sunlight to electricity? Better catalysts for producing clean hydrogen fuel? Stronger, lighter materials for aircraft? All of these require quantum mechanical understanding that classical computers struggle to provide. Quantum computers could simulate materials atom by atom, revealing why they behave as they do and suggesting modifications to improve them. You could test thousands of potential material compositions, virtually, before ever making them in a lab. The impact could be transformative across industries from energy to transportation to construction. Financial services is already heavily invested in quantum computing research. Banks and investment firms deal with incredibly complex optimization problems. How do you construct a portfolio that maximizes returns while minimizing risk across thousands of assets and market conditions? How do you price complex derivatives that depend on multiple uncertain factors? How do you detect fraudulent transactions among billions of legitimate ones? These problems involve searching through vast solution spaces or performing Monte Carlo simulations that require enormous computational resources. Quantum computers could potentially solve optimization problems faster, find better trading strategies, price derivatives more accurately, or detect subtle patterns indicating fraud. J.P. Morgan Chase, Goldman Sachs, and other major financial institutions have quantum computing research teams exploring these applications. However, there's healthy skepticism about near-term impact. Many financial optimization problems have good classical solutions, and it's unclear whether quantum computers will offer sufficient advantages to justify their cost and complexity. The most promising applications might be in areas like risk analysis and fraud detection, where finding subtle patterns in complex data is crucial. Cryptography and cybersecurity present both threats and opportunities. We've discussed how Shor's algorithm threatens RSA encryption, but the implications go deeper. Much of modern internet security relies on mathematical problems, like factoring and discrete logarithms, that quantum computers can solve efficiently. When large-scale quantum computers arrive, current encryption standards will become obsolete. This has sparked development of post-quantum cryptography, new encryption schemes based on mathematical problems that even quantum computers can't solve efficiently. Lattice-based cryptography, hash-based signatures, and other approaches are being standardized to replace vulnerable systems. The race is on to transition critical systems to quantum-resistant encryption before quantum computers become powerful enough to break current encryption. But quantum computers also enable new security approaches. Quantum key distribution uses the principles of quantum mechanics to create provably secure communication channels. Any attempt to intercept the quantum states used for key exchange disturbs them in detectable ways, alerting the communicating parties. While not requiring full quantum computers, This quantum technology could create unhackable communication networks. Artificial intelligence and machine learning are areas of intense speculation. Could quantum computers accelerate AI development? The answer is complicated. Many machine learning tasks involve linear algebra operations on large matrices, and some quantum algorithms can speed these up. Training neural networks, optimizing models, and finding patterns in high-dimensional data might benefit from quantum speedups. Companies like Google, IBM, and startups are exploring quantum machine learning, testing whether quantum computers can find patterns in data that classical computers miss or train models more efficiently. Early results are mixed. For some problems, quantum approaches show promise. For others, classical methods remain superior. It's likely that quantum machine learning will find niches where it excels rather than replacing classical machine learning entirely. One intriguing possibility is using quantum computers to develop better AI for scientific discovery. Imagine quantum computers simulating complex quantum systems, while AI analyzes the results to extract patterns and insights. The combination could accelerate scientific progress in chemistry, physics, and materials science. Logistics and supply chain optimization is another application area. Companies like FedEx, UPS, and Amazon deal with staggeringly complex optimization problems. How do you route thousands of vehicles to deliver millions of packages using minimal fuel and time? How do you manage inventory across hundreds of warehouses? How do you schedule flights and crews for airlines? These are combinatorial optimization problems where the number of possible solutions grows exponentially with problem size. Current solutions use sophisticated classical algorithms and often accept good enough answers rather than optimal ones. Quantum computers, particularly quantum annealers, might find better solutions faster. Volkswagen has explored quantum optimization for traffic flow management. Airlines have looked at quantum approaches for scheduling. However, the jury is still out on whether quantum advantages will materialize for these problems. Many logistics problems have additional constraints and real-world messiness that quantum algorithms might struggle with. And classical optimization has had decades of refinement, setting a high bar for quantum approaches to beat. Climate modeling and weather prediction could benefit from quantum simulation. Climate is a complex system involving atmospheric physics, ocean currents, ice dynamics, and countless feedback loops. More accurate climate models require simulating these systems at finer resolutions, which is computationally expensive. Quantum computers might simulate aspects of climate systems more efficiently, improving long-term climate predictions and helping us understand and mitigate climate change. Similarly, weather forecasting could improve with quantum computing. Weather is notoriously chaotic, where small uncertainties in initial conditions lead to large uncertainties in predictions. Running many simulations with slightly different starting conditions helps quantify uncertainty. Quantum computers might run these ensemble forecasts more efficiently, extending the reliable prediction horizon from days to weeks. Energy optimization is crucial as we transition to renewable energy. Solar and wind power are intermittent, requiring sophisticated management of energy storage, distribution, and demand. Quantum computers could optimize power grids, determining when to store energy, when to release it, and how to route it to minimize costs and ensure reliability. They could help design better batteries by simulating electrochemistry at the quantum level. The automotive industry is investing heavily in quantum computing research. Besides materials for lighter vehicles and batteries for electric cars, there's interest in optimization for manufacturing processes, supply chains, and even autonomous vehicle routing. BMW, Daimler, and other manufacturers have quantum computing partnerships exploring these applications. Telecommunications companies are interested in network optimization. How do you route data through complex networks to minimize latency and maximize throughput? How do you allocate radio spectrum efficiently? These optimization problems might benefit from quantum approaches. Pharmaceutical companies aren't just interested in drug discovery. They're also looking at quantum computing for protein folding, understanding how chains of amino acids fold into three-dimensional protein structures. Misfolded proteins cause diseases like Alzheimer's and Parkinson's. Understanding folding could lead to new treatments. Quantum computers might simulate protein folding more accurately than classical approaches. Agriculture could benefit from quantum-designed fertilizers and pesticides. Current fertilizer production is energy-intensive and environmentally damaging. Quantum simulations might help design better catalysts for nitrogen fixation, making fertilizer production more efficient. Quantum-designed pesticides could be more targeted and less harmful to non-pest species. Space exploration might use quantum computers for trajectory optimization, communication protocols, or simulating exotic physics in extreme environments. NASA and other space agencies are monitoring quantum computing developments. National security applications are largely classified, but it's clear that governments view quantum computing as strategically important. Beyond cryptography, there might be applications in intelligence analysis, logistics for military operations, or simulating weapon systems. It's important to maintain perspective. Many of these applications are still speculative. We don't yet have quantum computers powerful enough to deliver clear advantages over classical approaches for most real-world problems. Current quantum computers are research tools, valuable for learning and exploring, but not yet practical for production use in most industries. The timeline for impact varies by application. Quantum chemistry and material simulation might see practical results within 5 to 10 years as quantum computers reach hundreds of reliable logical qubits. Breaking current encryption might require a decade or more and thousands of logical qubits. Some applications might never materialize if classical algorithms improve faster than quantum hardware. There's also the question of accessibility. Will quantum computing be available only to large corporations and governments, or will smaller companies and researchers have access? Cloud quantum computing services from IBM, Amazon, Google, and others are democratizing access, allowing anyone to experiment with quantum algorithms. This could lead to unexpected applications discovered by researchers who bring fresh perspectives. The economic impact could be enormous. Some estimates suggest quantum computing could generate trillions of dollars in value across industries over coming decades. But predicting the exact impact is difficult. History shows that transformative technologies often create value in unexpected ways. The Internet's biggest applications weren't predicted by early researchers. Quantum computing may similarly surprise us. What's clear is that multiple industries are investing heavily because they believe quantum computing will matter. Whether it's pharmaceutical companies pursuing new drugs, financial firms seeking trading advantages, or technology companies exploring new capabilities, the race to find quantum applications is intensifying. As hardware improves and algorithms mature, we'll discover which applications deliver real value and which remain theoretical possibilities. The next decade will be crucial in determining quantum computing's true impact on the world. The race to build practical quantum computers is one of the most intense technological competitions in history. Billions of dollars are being invested, thousands of researchers are involved, and the stakes couldn't be higher. Let's look at who's leading this race and where we stand today. IBM has been at the forefront of quantum computing for decades. They've made quantum computing accessible through the IBM Quantum Experience, a cloud platform where anyone can run quantum programs on real quantum hardware. Their approach uses superconducting qubits, and they've steadily increased qubit counts and improved performance. In 2023, they unveiled a 433-qubit processor called Osprey, and they're working toward systems with thousands of qubits. What sets IBM apart is their focus on building a complete quantum computing ecosystem. They've developed Qiskit, one of the most popular quantum programming frameworks. They're working on modular quantum computing, where multiple quantum processors work together. They've created detailed roadmaps showing how they plan to achieve fault-tolerant quantum computing by the end of this decade. IBM isn't just building hardware. They're building the entire infrastructure needed for practical quantum computing. Google made headlines in 2019 with their quantum supremacy announcement. Their Sycamore processor, with 53 superconducting qubits, performed a specific calculation in 200 seconds that they claimed would take the world's most powerful supercomputer 10,000 years. IBM disputed the exact numbers, suggesting it might only take a few days with better classical algorithms. But the achievement was still remarkable. It demonstrated that quantum computers could outperform classical computers on at least some tasks. Google's approach emphasizes quality over quantity. Rather than maximizing qubit count, they focus on reducing error rates and improving gate fidelities. They're heavily invested in developing error correction and see themselves on a path to building a million-qubit, fault-tolerant quantum computer capable of practically useful calculations. Their parent company Alphabet provides substantial resources, allowing them to pursue ambitious long-term goals. Amazon isn't building quantum computers themselves, but they're becoming a major player through Amazon Web Services Breakit, their quantum computing cloud service. Breakit provides access to quantum computers from multiple vendors, including D-Wave, IonQ, and Rigetti. This platform approach allows researchers and companies to experiment with different quantum technologies without committing to a single vendor. Amazon is also investing in quantum networking and quantum error correction research. Microsoft has taken a different and riskier approach. They're betting on topological qubits, a technology that doesn't fully exist yet. Topological qubits would encode information in exotic quantum states that are inherently protected from certain types of errors, potentially eliminating the need for some error correction overhead. Microsoft has world-class theorists and has made progress on the underlying physics, but they don't yet have a functional topological qubit. If they succeed, they could leapfrog competitors. If not, they may find themselves far behind. Meanwhile, Microsoft has developed excellent quantum programming tools. Their Q-Sharp language and Quantum Development Kit are sophisticated platforms for writing and testing quantum programs. They offer Azure Quantum, a cloud service providing access to multiple quantum computing technologies. Even without their own quantum hardware yet, they're positioning themselves as a key player in the quantum software ecosystem. Intel brings semiconductor manufacturing expertise to quantum computing. They're exploring superconducting qubits, but are particularly interested in silicon spin qubits, which encode quantum information in electron spins in silicon. This approach could potentially leverage existing semiconductor fabrication infrastructure, making it easier to manufacture quantum processors at scale. Intel spin qubits operate at slightly higher temperatures than superconducting qubits, which could simplify refrigeration requirements. IonQ is a leading startup in trapped ion quantum computing. Founded by researchers from the University of Maryland, they've built systems that are accessible via cloud platforms, including Amazon Breakit, Microsoft Azure, and Google Cloud. Their trapped ion approach offers high-fidelity gates and long coherence times. IonQ has gone public, giving them capital to scale up their technology. They're working on networking multiple ion traps together to increase computational power. Rigetti Computing is another significant player in superconducting quantum computing. They've developed their own quantum processors and offer cloud access through their Quantum Cloud Services platform. Rigetti focuses on hybrid quantum classical algorithms, recognizing that near-term quantum computers will work best when integrated with classical computing resources. They're also developing specialized control systems and quantum classical interfaces. Honeywell, now merged with Cambridge Quantum Computing to form Quantinuum, brings precision engineering expertise to trapped ion quantum computing. Their systems achieve very high fidelities and low error rates. Quantinuum is pursuing both hardware development and quantum software, including quantum chemistry applications and quantum natural language processing. The merger brought together hardware capability with software and algorithm expertise. D-Wave has pioneered quantum annealing, a specialized form of quantum computing for optimization problems. Their systems have thousands of qubits, far more than gate-based quantum computers, but they're not universal quantum computers. They can't run Shor's algorithm or general quantum circuits. However, for specific optimization tasks, quantum annealing might offer advantages. D-Wave has commercial customers using their systems for real problems, though debate continues about whether they're truly outperforming classical approaches. Xanadu is pursuing photonic quantum computing from Canada. They've developed a cloud-accessible photonic quantum computer and created Pennylane, a software library for quantum machine learning. Photonic approaches have advantages like room temperature operation and compatibility with existing fiber optic infrastructure. Xanadu is exploring how photonic quantum computers might address specific problems where their architecture naturally fits. PsiQuantum, also focused on photonic quantum computing, has raised over $600 million in funding, one of the largest amounts in the field. They're taking an all-or-nothing approach, planning to build a fault-tolerant quantum computer with 1 million qubits, rather than releasing smaller intermediate systems. They believe photonics is the only path to truly scalable quantum computing and are building the fabrication capabilities to produce the vast numbers of components required. China has made quantum technology a national priority. The University of Science and Technology of China, led by physicist Pan Jianwei, has demonstrated impressive achievements, including quantum teleportation records and the Zhejiang photonic quantum computer that claimed quantum computational advantage for a specific problem. China is investing billions in quantum research and has launched quantum communication satellites. The geopolitical dimensions of quantum computing are significant, with quantum capability viewed as strategic. The European Union has launched a quantum flagship initiative with funding exceeding €1 billion. Research institutions across Europe are working on various quantum computing approaches. Companies like Alpine Quantum Technologies in Austria and IQM in Finland are developing quantum computers. Europe sees quantum technology as crucial for maintaining technological competitiveness. National labs in the United States, including Oak Ridge, Argonne, and Los Alamos, have quantum computing programs. They're exploring applications in nuclear physics, materials science, and other areas relevant to their missions. They're also developing the classical computing infrastructure needed to control quantum computers and process results. Universities remain central to quantum computing research. MIT, Caltech, University of Maryland, Yale, and many others have leading quantum computing programs. Academic research produces many of the breakthroughs that companies then commercialize. The relationship between academia and industry is symbiotic, with companies often hiring academic researchers and funding university projects. Startups are proliferating. Companies are working on quantum software, quantum algorithms for specific industries, quantum networking, quantum sensors, control systems, and countless other aspects of the quantum ecosystem. Venture capital has poured billions into quantum technology, betting that the field is approaching practical utility. Where do we actually stand today? Current quantum computers have reached the point where they can perform calculations that strain classical computers, at least for specifically designed problems. Google's quantum supremacy demonstration, while disputed in its details, showed genuine quantum computational advantage. More recently, researchers have demonstrated quantum advantage for other tasks. However, these are still narrow demonstrations on artificial problems. For practical, real-world problems that people actually care about solving, classical computers generally still win. Current quantum computers are in what researchers call the NISQ era, noisy intermediate-scale quantum. They have enough qubits to be interesting, typically 50 to a few hundred, but not enough for error correction. They're noisy, with error rates that limit how complex an algorithm you can run. They're intermediate, bigger than early prototypes, but smaller than the fault-tolerant machines we'll eventually need. Qubit count has been increasing steadily. 5 years ago, 50 qubits was impressive. Now systems with hundreds of qubits exist. IBM's roadmap shows them targeting thousands of physical qubits in the next few years. But raw qubit count isn't everything. Quality matters more. A system with 50 high-fidelity, well-connected qubits might be more useful than one with 500 noisy, poorly connected qubits. Error rates have been improving. Gate fidelities, the accuracy of quantum operations, have risen from 90% to over 99% for the best systems. 2-qubit gates, which are harder, have also improved dramatically. Coherence times have extended from microseconds to milliseconds for some systems. These incremental improvements compound over time, making quantum computers progressively more capable. Error correction remains the grand challenge. Demonstration of basic error correction codes on small numbers of qubits has been achieved. Researchers have shown they can detect and correct errors without destroying quantum information. But scaling to the thousands or millions of physical qubits needed to create hundreds of fault-tolerant logical qubits is still years away. Most experts believe the late 2020s or early 2030s might see the first truly fault-tolerant quantum computers. Cloud access has democratized quantum computing. Researchers anywhere can run experiments on real quantum hardware without building their own. This has accelerated research and education. Universities teach quantum computing courses where students program real quantum computers. Thousands of researchers are exploring algorithms and applications. This broad participation increases the chances of breakthrough discoveries. Commercially, we're seeing early adoption in specific niches. Pharmaceutical and chemical companies are exploring quantum simulation for drug discovery and materials design. Financial firms are testing quantum approaches for optimization and risk analysis. Even if quantum computers aren't yet faster than classical alternatives, companies are investing to develop expertise and be ready when quantum advantage arrives. The timeline to transformative impact remains uncertain. Optimists believe we're 5 to 10 years from quantum computers solving problems no classical computer can handle practically. Pessimists think it might be 20 years or more. Much depends on how quickly error correction can be implemented at scale and whether any unforeseen obstacles emerge. What's clear is that the field is moving faster than many predicted. A decade ago, 50 qubits seemed distant. Today we're discussing systems with thousands. Companies are investing billions because they believe quantum computing will deliver massive value. Governments are funding quantum research as a strategic priority. The momentum is undeniable. The quantum computing race isn't winner-take-all. Different approaches might excel for different problems. Superconducting qubits might be best for some applications, trapped ions for others, photonic quantum computers for networking. We might see a heterogeneous future where multiple quantum computing technologies coexist, each optimized for specific tasks, integrated with classical computing into hybrid systems that leverage the best of both worlds. The race isn't over. In many ways, it's just beginning. Let's look beyond the current state of quantum computing and imagine what the future might hold. Some of these possibilities are extensions of what we know quantum computers can do. Others are more speculative, representing the outer edges of what might become possible. But all of them give us a glimpse of how profoundly quantum computing could reshape our world. The quantum internet is perhaps the most ambitious near-term vision. Imagine a global network where quantum information can be transmitted between quantum computers, enabling distributed quantum computing and perfectly secure communication. This isn't just faster internet. It's fundamentally different, using quantum entanglement to connect nodes. In a quantum internet, you could entangle qubits across vast distances, creating quantum networks where multiple quantum computers work together on the same problem. You could perform quantum teleportation, transmitting quantum states from one location to another without the information traveling through the space between. You could achieve quantum key distribution on a global scale, making communication provably secure against any eavesdropper, even one with the quantum computer. The technical challenges are enormous. Quantum states are fragile and don't survive long in optical fibers. You need quantum repeaters, devices that can extend quantum communication over long distances without destroying entanglement. You need quantum memories that can store quantum states while coordinating network operations. Despite these challenges, prototype quantum networks already exist. China has launched quantum communication satellites. Research networks in Europe and the United States are testing quantum networking technologies. The foundation for a quantum internet is being laid. What could you do with a quantum internet? Imagine globally distributed quantum sensors that share quantum entanglement, achieving measurement precision impossible with classical networks. Imagine secure voting systems where quantum mechanics guarantees ballot integrity. Imagine scientific collaborations where researchers worldwide share access to quantum computing resources, working together on problems too large for any single quantum computer. Looking further ahead, quantum computing might merge with artificial intelligence in transformative ways. We've discussed quantum machine learning, but imagine something deeper. What if artificial general intelligence, AI that matches or exceeds human intelligence across all domains, requires quantum computing? Human brains might exploit quantum effects in ways we don't fully understand. Creating artificial minds with similar capabilities might require quantum hardware. Even without that speculative leap, quantum-enhanced AI could be remarkable. Imagine AI systems that can explore vast solution spaces instantaneously, that can recognize patterns in data no classical system could find, that can optimize themselves using quantum algorithms. These systems might accelerate scientific discovery exponentially, finding connections and insights that human researchers would never see. They might design new technologies, solve problems we haven't even formulated yet, and push the boundaries of knowledge in every field. Quantum simulation could reveal entirely new physics. By simulating quantum systems more complex than we can study experimentally, quantum computers might predict new phenomena, new phases of matter, new particles. They might help us understand high-temperature superconductivity, a phenomenon that's puzzled physicists for decades. They might simulate the early universe, revealing how matter and energy behaved in the first moments after the Big Bang. They might probe the quantum nature of gravity, potentially helping unify quantum mechanics and general relativity. In medicine, quantum computing could enable truly personalized medicine. Imagine simulating not just how a drug interacts with a protein, but how it affects an entire biological system, accounting for an individual's unique genetics, metabolism, and physiology. Quantum computers could design custom therapies optimized for each patient, predicting side effects and outcomes with unprecedented accuracy. They could simulate entire organs or even simplified versions of the human body, enabling virtual clinical trials before testing on real patients. Quantum computers might help us understand consciousness, perhaps the deepest mystery in science. If quantum effects play a role in how brains generate subjective experience, quantum simulations might reveal those mechanisms. This could transform neuroscience, psychiatry, and our fundamental understanding of what it means to be conscious. Climate change mitigation could benefit enormously from quantum computing. Imagine simulating Earth's entire climate system at molecular resolution, capturing every feedback loop and interaction. This could give us century-long forecasts with unprecedented accuracy, showing exactly how different policy choices affect the climate. Quantum computers could design better carbon capture systems, more efficient solar cells, revolutionary energy storage, and climate-resistant crops. The stakes couldn't be higher, and quantum computing might give us tools to address them. Space exploration could be transformed. Quantum computers on spacecraft could navigate autonomously using quantum sensing and optimization. They could analyze data from distant planets in real time. They could help design fusion propulsion systems for interstellar travel by simulating plasma physics at quantum scales. They could potentially enable communication across vast cosmic distances using quantum entanglement, though this remains highly speculative and might violate fundamental physics. The economic implications are staggering. Some estimates suggest quantum computing could create tens of trillions of dollars in value across industries. Entire new industries might emerge around quantum technologies. Just as classical computing created companies like Microsoft, Apple, Google, and Amazon, quantum computing might spawn entirely new economic ecosystems. The countries and companies that lead in quantum computing could gain enormous advantages in technology, economy, and security. But with great power comes great responsibility, and quantum computing raises profound ethical questions. The ability to break current encryption could enable mass surveillance on an unprecedented scale. Authoritarian governments could use quantum computers to monitor citizens, suppress dissent, and maintain control. Even democratic governments might face temptations to use quantum computing for surveillance beyond what's ethically acceptable. The weaponization of quantum computing is another concern. Could quantum computers design new weapons, biological or chemical agents, or cyber weapons of unprecedented sophistication? Could they optimize military strategy in ways that make conflict more likely or more destructive? These aren't hypothetical concerns. Military applications are being researched by multiple nations. There's also the question of access and equity. If quantum computing delivers transformative capabilities, who gets to use them? Will they be available only to wealthy nations and large corporations, exacerbating existing inequalities? Or will they be democratized, allowing researchers and companies everywhere to benefit? The answers to these questions will shape whether quantum computing amplifies inequality or helps address global challenges. Quantum computing might also challenge our understanding of computation itself. Church-Turing thesis suggests that any effectively calculable function can be computed by a classical computer. Quantum computers don't violate this in a strict sense. They're still Turing machines in the formal definition, but they might compute things efficiently that classical computers cannot, revealing that practical computability is richer than we thought. This could have philosophical implications for questions about the nature of information, complexity, and what problems are truly solvable. Some physicists speculate about even wilder possibilities. Could we use quantum computers to simulate universes? Not just models, but actual universes with their own laws of physics, running as quantum simulations? This ventures into philosophy and metaphysics, but quantum simulation is, in a sense, creating a quantum system that behaves like another quantum system. The boundaries between simulation and reality become blurry at quantum scales. There's also quantum supremacy in new domains. We've achieved it for specific sampling tasks. Where else might quantum computers demonstrate insurmountable advantages? Cryptography beyond just factoring? Quantum chemistry beyond small molecules? Optimization problems in logistics, finance, or engineering? Each new domain where quantum computers prove superior expands their impact and justifies further investment. The timeline for these possibilities varies enormously. The quantum internet might see substantial deployment within a decade. Quantum-enhanced drug discovery might happen within 5 to 15 years. Breaking encryption might require 10 to 20 years or more. True artificial general intelligence, if quantum computing plays a role, could be decades away. Understanding consciousness through quantum simulation might be a century away or might never happen. Some of these futures are certain, or at least highly probable. We will have quantum networks. We will use quantum simulation for chemistry and materials. Others are speculative, depending on breakthroughs we can't guarantee. We might never achieve quantum artificial general intelligence if brains don't fundamentally require quantum effects. We might find that quantum computers, despite their power, can't solve certain problems we hope they could. What's exciting is that we're on the cusp of finding out. The next 10 to 20 years will reveal which quantum computing applications deliver real value and which remain theoretical possibilities. We'll discover new algorithms and applications we haven't imagined. We'll face ethical and security challenges that require thoughtful governance. We'll see quantum computing transition from research labs to commercial reality. The future isn't predetermined. The choices we make now about quantum computing development, access, governance, and application will shape what quantum computing becomes. We can steer toward futures where quantum computing addresses global challenges, accelerates human flourishing, and expands knowledge. Or we can stumble toward futures where quantum computing amplifies inequality, enables surveillance, and creates new risks. One thing seems certain: quantum computing will be transformative. Whether that transformation is primarily positive or creates new problems depends on how we develop and deploy this technology. The quantum revolution isn't just about building faster computers. It's about harnessing fundamental physics to expand what's computationally possible, and in doing so, expanding what humanity itself can achieve. The most mind-blowing possibility isn't any specific application. It's that quantum computing might reveal entirely new ways of thinking about information, computation, and problem-solving. Just as classical computing transformed society in ways early pioneers never imagined, quantum computing might transform society in ways we can't currently foresee. We're not just building tools. We're opening doors to realms of possibility we're only beginning to glimpse. The future of quantum computing is being written right now, in laboratories and boardrooms and policy discussions around the world. It's a future full of promise and peril, of opportunities and challenges. And remarkably, if you're watching this, you're witnessing the early chapters of this quantum revolution. The decisions made in the next decade will echo for generations. The applications developed will reshape industries. The discoveries made will expand human knowledge. We're living through one of the great technological transitions in history, and the quantum future is just beginning. Quantum computing is surrounded by hype, misconceptions, and outright myths. Let's clear up some of the most common misunderstandings and separate reality from science fiction. Understanding what quantum computers can't do is just as important as understanding what they can. The biggest myth is that quantum computers are just faster versions of classical computers. This is fundamentally wrong. Quantum computers aren't universally faster. They're differently fast. For many tasks, classical computers are superior and always will be. Quantum computers excel at specific types of problems, where quantum properties like superposition and interference can be exploited. For everything else, your laptop is just fine. Want to browse the web, write documents, edit photos, or play most video games? A quantum computer won't help. These tasks don't have the mathematical structure that quantum algorithms can exploit. A quantum computer running a word processor would be like using a Formula One race car for grocery shopping. Technically possible, absurdly impractical, and completely missing the point. Another common misconception is that quantum computers can try all possible solutions simultaneously and instantly find the right answer. This misunderstands how quantum computing works. Yes, qubits exist in superposition of multiple states. Yes, this represents exploring multiple possibilities simultaneously. But extracting the answer requires careful algorithm design that uses interference to amplify correct answers while canceling wrong ones. And measurement is probabilistic. You might need to run the algorithm multiple times to get reliable results. Some people think quantum computers will make classical computers obsolete. Not even remotely true. Quantum computers are specialized processors for specific problem types. Classical computers will continue to dominate general-purpose computing. The future is hybrid systems where classical computers handle most tasks and quantum computers accelerate specific calculations. It's like how graphics processing units complement central processing units in modern computers. Quantum processors will be another specialized component, not a replacement. There's a myth that quantum computers already exist and are being used widely. Reality is more nuanced. Quantum computers exist. You can access them via cloud services, but they're research instruments and early prototypes, not production systems. Current quantum computers are small, noisy, and limited. They're valuable for learning and exploring, but they're not yet solving real-world problems better than classical computers for most applications. We're in the early stages, not the mature deployment phase. Some believe quantum computing will break all encryption immediately. The truth is more complex. Quantum computers threaten specific encryption schemes based on factoring and discrete logarithms, like RSA and elliptic curve cryptography. But they don't break all encryption. Symmetric encryption like AES remains secure. You just need longer keys. And post-quantum cryptography is being developed specifically to resist quantum attacks. The transition to quantum-resistant encryption is happening now, well before large-scale quantum computers arrive. Moreover, breaking encryption requires fault-tolerant quantum computers with thousands of logical qubits running complex algorithms for hours. We're years, possibly decades, from that capability. Current quantum computers can't threaten any real encryption. The threat is future quantum computers, giving us time to prepare. There's confusion about quantum supremacy or quantum advantage. Some think these terms mean quantum computers are now better than classical computers generally. Actually, they refer to narrow demonstrations on specifically designed problems. Google's quantum supremacy experiment showed their quantum computer could perform one particular calculation faster than classical computers. But that calculation has no practical application. It was a milestone proving quantum computers can outperform classical computers on something, but not a sign that quantum computers are broadly superior. Some people think quantum entanglement enables faster-than-light communication. This is absolutely false and violates fundamental physics. Entanglement creates correlations between particles, but you can't use it to transmit information faster than light. When you measure one entangled particle, the other state is determined, but that doesn't let you send messages. Quantum communication using entanglement still requires classical communication channels and obeys the speed of light limit. There's a belief that quantum computers work by accessing parallel universes. This comes from the many worlds interpretation of quantum mechanics, which suggests that superposition represents the quantum state existing in multiple parallel realities. While this is one interpretation of quantum mechanics, it's not necessary for quantum computing to work. You can understand and build quantum computers without believing in parallel universes. The mathematics of quantum mechanics is what matters, not any particular philosophical interpretation. Some think any problem that's hard for classical computers will be easy for quantum computers. Not true. Many hard problems don't have known quantum algorithms that offer significant speedups. NP-complete problems, a class of problems that includes many important optimization and search problems, don't generally have efficient quantum solutions. Quantum computers might offer modest speedups for some NP-complete problems, but not exponential speedups that make them trivial. There's confusion about when quantum computing will be practical. Timelines vary wildly from optimistic predictions of a few years to pessimistic estimates of decades. The truth is uncertain. For some applications, like quantum chemistry simulation, we might see practical advantages within 5 to 10 years. For others, like breaking encryption, it might be 15 to 20 years or more. And some hope for applications might never materialize if quantum algorithms don't provide sufficient advantages. Some believe quantum computers can solve undecidable problems or perform infinite calculations. This is impossible. Quantum computers are still bound by the fundamental limits of computation. They can't solve problems that are mathematically undecidable. They can't compute uncomputable functions. They're powerful, but they're not magic. They operate within the same theoretical framework as classical computers, just with different complexity classes for certain problems. There's a myth that quantum computers always give exact answers. In reality, quantum algorithms are often probabilistic. They give the correct answer with high probability, but not certainty. Running the algorithm multiple times and taking the most common answer increases confidence. Error correction in fault-tolerant quantum computers will improve this. But some irreducible uncertainty remains in quantum mechanics itself. People sometimes think quantum computers don't make errors or that quantum states are perfectly stable. Quite the opposite. Current quantum computers are extremely noisy. Qubits decohere rapidly. Gates have significant error rates. This is why error correction is so crucial and why building fault-tolerant quantum computers is so challenging. Quantum states are among the most fragile things in nature. Some believe that quantum computing means the end of privacy or that all data ever encrypted is now vulnerable. Current encrypted data is safe from current quantum computers. Future quantum computers might threaten encryption schemes in use today, but only if that data is still valuable when quantum computers become powerful enough. Moreover, quantum-resistant encryption will protect new data, and some encryption, like symmetric encryption with sufficient key lengths, remains secure even against quantum attacks. There's confusion about quantum computers and quantum mechanics generally. Some think quantum computing proves consciousness is quantum, or that it validates mystical interpretations of quantum mechanics. Quantum computing is applied physics and engineering. It doesn't prove anything about consciousness, spirituality, or metaphysics. It uses quantum mechanical effects to perform calculations. That's it. The philosophical implications of quantum mechanics are separate from the practical applications. People sometimes think quantum computers will be consumer products, that you'll buy a quantum laptop or quantum phone. Extremely unlikely. Quantum computers require extreme conditions, like near absolute zero temperatures or ultra-high vacuums. They need sophisticated control systems and shielding. They're not miniaturizing to consumer devices anytime soon. Access will be primarily through cloud services, with quantum processors in specialized facilities while you access them remotely. Some believe quantum computing is purely theoretical or that quantum computers are impossible to build. We've definitively disproven this. Quantum computers exist, they work, and you can use them today via cloud services. They're limited and noisy, but they're real. The question isn't whether quantum computers are possible, but how powerful we can make them and how quickly. There's a myth that quantum computing is only about qubits, and that more qubits always means better. Quality matters more than quantity. 100 high-quality, low-error, well-connected qubits can be far more useful than 1,000 noisy, poorly connected qubits. Metrics like gate fidelity, coherence time, connectivity, and error rates are at least as important as qubit count. Some think quantum computers will solve climate change, cure all diseases, or solve humanity's greatest challenges automatically. Quantum computers are tools. Powerful tools, potentially transformative tools, but still tools. They might accelerate solutions to these challenges by enabling better simulations, optimizations, and discoveries. But they won't solve complex problems that involve human behavior, politics, economics, and ethics. Technology alone never solves everything. Finally, there's excessive hype that quantum computing will transform everything immediately. Reality is that quantum computing will likely transform many things eventually. The timeline is uncertain, the path is complex, and there will be setbacks and surprises. Maintaining realistic expectations while still pursuing ambitious goals is crucial. Understanding these myths and misconceptions helps set appropriate expectations. Quantum computing is genuinely revolutionary for specific applications. It's not magical, it's not universally superior, and it's not arriving tomorrow to replace all computing. It's an emerging technology with enormous potential and significant challenges. Appreciating both the promise and the limitations leads to better decisions about how to develop, deploy, and regulate quantum computing. The reality of quantum computing is fascinating enough without exaggeration. We don't need hype. We just need understanding. We've journeyed through the remarkable world of quantum computing, from the strange principles of quantum mechanics to the cutting-edge hardware being built today, from powerful algorithms to transformative applications, from the major players racing to build these machines to the mind-bending possibilities of the future. Now let's bring it all together and understand what quantum computing really means for you and for humanity. Quantum computing represents one of the most profound technological shifts in human history. We're not just building faster computers. We're learning to harness the fundamental laws of the universe itself to solve problems that have been beyond our reach. We're taking phenomena that Einstein called spooky, effects that seem to violate common sense, and turning them into practical tools for discovery and innovation. Think about the journey we've described. We started with quantum mechanics, where particles exist in superposition, where distant objects can be entangled, where observation fundamentally changes reality. These aren't philosophical abstractions. They're experimentally verified facts about how our universe works at the smallest scales. And quantum computing is our attempt to exploit these facts for computation. We've seen how quantum computers are built, from superconducting circuits cooled to near absolute zero to ions trapped in vacuum and manipulated with lasers, from photons guided through integrated circuits to exotic topological states that might revolutionize error correction. Each approach faces enormous engineering challenges, yet multiple approaches are succeeding. The hardware exists. It's improving rapidly. What seemed impossible a decade ago is routine today. We've explored quantum algorithms that offer exponential speedups for factoring, quadratic speedups for searching, and efficient simulation of quantum systems that classical computers simply cannot match. These algorithms aren't just theoretical curiosities. They're being tested on real quantum hardware. They're being refined and improved. New algorithms are being discovered constantly as researchers explore what quantum computers can do. We've looked at applications across industries. Drug discovery that could save millions of lives. Materials design that could solve energy and environmental challenges. Financial optimization that could make markets more efficient. Cryptography that requires completely rethinking how we secure information. Artificial intelligence that might be enhanced by quantum capabilities. The potential impact spans virtually every field of human endeavor. We've seen who's building quantum computers, from tech giants like IBM and Google to innovative startups like IonQ and Rigetti, from governments investing billions to universities training the next generation of quantum scientists and engineers. The quantum computing ecosystem is vibrant, competitive, and global. The race is on, and the stakes couldn't be higher. We've imagined futures where quantum internet connects the world with provably secure communication, where quantum-enhanced AI accelerates discovery, where personalized medicine tailors treatments to individuals, where we understand consciousness and climate and the fundamental nature of reality in ways currently impossible. Some of these futures are years away. Others are decades away. Some might never arrive, but all represent genuine possibilities. And we've cleared up misconceptions, understanding that quantum computers aren't magic, aren't universally faster, and won't arrive tomorrow to solve all problems instantly. They're specialized tools for specific types of calculations, incredibly powerful within their domain, but not replacements for classical computing. Setting realistic expectations while still appreciating the genuine potential is crucial. So where does this leave us? Quantum computing is transitioning from research to reality. We're past the point of wondering whether it's possible. The question now is how quickly we can scale it up, how effectively we can apply it, and how wisely we can govern it. The next decade will be crucial. For researchers and students, quantum computing offers extraordinary opportunities. This is a field being built right now. Fundamental questions remain open. New algorithms wait to be discovered. Applications in every industry need exploring. If you're drawn to physics, mathematics, computer science, or engineering, quantum computing needs you. The field is young enough that individual contributions can still make enormous impacts. For business leaders and policymakers, quantum computing requires attention and preparation. The companies and countries that lead in quantum technology will have significant advantages. But leadership requires investment, patience, and strategic thinking. It means supporting research, developing talent, building infrastructure, and creating frameworks for responsible development and use. For everyone else, quantum computing might seem distant and abstract, but its impacts will be concrete and personal. The medicines you take, the security of your data, the technologies available to you, all could be shaped by quantum computing in coming decades. Understanding at least the basics of this technology helps you make informed decisions and appreciate the changes coming. What can you do right now? If you're technically inclined, start learning. Quantum computing courses are available online, many for free. Platforms like IBM Quantum Experience let you program real quantum computers from your browser. Books, tutorials, and communities exist to support learners at every level. The barrier to entry has never been lower. If you're in a position to invest or allocate resources, consider quantum computing's potential. Not hype-driven investment in whatever's trendy, but thoughtful investment in companies and projects with solid technical foundations and realistic timelines. The field needs patient capital that understands the challenges and opportunities. If you're in education, consider how to prepare students for a quantum future. Quantum literacy, at least understanding the basic concepts, could become as important as computer literacy is today. Integrating quantum concepts into physics and computer science curricula helps build the workforce that quantum computing will need. If you care about ethics and governance, engage with the questions quantum computing raises. How do we ensure equitable access? How do we prevent misuse? How do we balance innovation with security? How do we transition to post-quantum cryptography before encryption-breaking quantum computers arrive? These aren't just technical questions. They're societal questions requiring broad participation. The quantum revolution is happening whether we're ready or not. The physics is sound. The engineering is progressing. The applications are emerging. The investments are flowing. The talent is developing. The infrastructure is being built. This isn't speculation about a distant future. This is present reality accelerating toward transformative impact. History shows that transformative technologies often develop faster than people expect once key thresholds are crossed. The Internet went from research project to ubiquitous infrastructure in remarkably few years. Smartphones went from novelty to necessity in about a decade. Quantum computing might follow a similar trajectory once fault-tolerant systems arrive. The time to understand, prepare, and engage is now, not after quantum computing has already transformed industries. We're living through a remarkable moment. We're witnessing the birth of a new computational paradigm based on exploiting the deepest laws of nature. We're seeing human ingenuity tackle extraordinary challenges and achieve things that seemed impossible. We're approaching capabilities that could reshape civilization. Quantum computing is more than just interesting technology. It's a testament to human curiosity and capability. It shows what's possible when we pursue fundamental understanding and apply it creatively. It demonstrates that even the strangest aspects of reality can be harnessed for practical purposes. It proves that we're still in the early stages of discovering what's possible with computation. The quantum future is not predetermined. It will be shaped by choices made by researchers, engineers, business leaders, policymakers, and citizens. It will reflect our values, our priorities, and our wisdom in developing powerful technologies. We can steer toward futures where quantum computing addresses humanity's greatest challenges and expands human flourishing. But that requires active engagement, not passive observation. Thank you for joining me on this journey through quantum computing. I hope you've gained understanding of this fascinating technology, appreciation for its potential, and realistic perspective on its challenges and timeline. Whether you become a quantum researcher, a quantum-aware business leader, or simply an informed citizen understanding one of the great technological developments of our time, you're now equipped to engage with the quantum revolution. The future is quantum, and that future is being built right now, one qubit at a time, by people around the world pushing the boundaries of what's possible. It's an exciting time to be alive, to witness this transformation, and perhaps to contribute to it. The quantum age is dawning. Let's make sure we're ready.